हेलो फ्रेंड्स, राना एकेडमी में आपका स्वागत है। हम देखने जा रहे थर्ड यूनिट ऑफ केमिस्ट्री ऑफ 11th क्लास, क्लासिफिकेशन ऑफ एलिमेंट्स एंड पीरियोडिसिटी इन प्रॉपर्टीज। The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests new advances of research for to professionals, and it provides the succinct succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities, but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of the chemistry, the chemical elements, says that Glenn T. Seberg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows as a biological consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. Why do we need to classify elements? We know by now that the elements are the basic units of all types of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known of them, and recently discovered elements are man-made efforts to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systemic way to organize their knowledge by classifying the elements. Not only that, it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. Genesis of periodic classification. Classification of elements into groups and development of periodic law and periodic table are the consequences of systematizing the knowledge gained by a number of scientists through their observations and experiments. The German chemist John Dobereiner in early 1800s was the first to consider the idea of trends among properties of elements. By 1829, he noted the similarity among the physical and chemical properties of several groups of three elements, trends, triads. In case of, and he noticed that the middle element of each of the triads has had an atomic weight of each of the and had an atomic weight of about halfway between the atomic weights of the other two. Table 3.1. Also, the properties of the middle element were in between those of the other two members, since Doberiner's on the periodic Doberiner's relationship referred to as the law of triads seemed to work only for a few elements. It was dismissed as coincidence. The next reported attempt to classify elements was made by a French dualist, A.E.B. de Chancotais in 1862. He arranged and the then no elements in order of increasing atomic weights and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist John Alexander Newlands in 1865 pre-founded the law of octaves. He arranged the elements in increasing order of their atomic weights and he noted that every The eighth element had properties similar to the first element, table 3.2. The relationship was just like a every eighth note that resembles the first in octaves of music. Newland's law of octaves seemed to be true only for elements up to calcium. Also, his idea was not widely accepted at that time. He for his work was later awarded Davy Medal in 1887 by the Royal Society, London. And the periodic law, as we know it today, owes its development to the Russian chemist Dmitry Mendeleev 1834 to 1907 and the German chemist Lothar Meyer 1832 and 1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point, and boiling point against atomic weight and obtained. Table 3.2 Newland's octaves. Lithium, beryllium, boron, carbon, nitrogen, oxygen, phoron, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium, calcium elements. A periodically repeated pattern, unlike Newland's, Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, a scientist who is generally credited with the development of the modern periodic table. While Doberan initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows: the properties of the elements are a periodic function of their atomic weights. Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements such with similar properties occupied the same vertical column or groups. Um, groups. Mendeleev's system of classifying elements was more elaborate than that of Luther Mayer's. He fully recognized the significance of periodicity and used a broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. He realized that some of the elements did not fit in with his scheme of classification. If the order of atomic weight was strictly followed, he ignored the order of atomic weights, thinking that the atomic measurements might be incorrect, and placed the elements with similar properties together. For example, iodine with lower atomic weight than that of tellurium. Group 6 was placed in Group 7 along with fluorine, chlorine, bromine because of similarities in properties. Figure 3.1 at the same time, keeping his primary aim of arranging the elements of similar properties in the same group. He proposed that some of the elements were still undiscovered and therefore left several gaps in the table. For example, both gallium and germanium were unknown at that time, and Mendeleev published his periodic table. He left the gap under aluminum and a gap under silicon and called these elements Ica aluminum and Ica silicon. Mendeleev predicted not only the existence of gallium and germanium, the but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements are and those found experimentally are listed in table 3.3. 3.3 Mendeleev's predictions for the elements Ica aluminum, gallium, and Ica silicon germanium. atomic weight, density, melting point, formula of oxide, formula of chloride. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table, published in 1905, is now shown in Figure 3.1. Periodic system of elements in groups and series. Groups of elements. Mendeleev's periodic table, published earlier. 3.3 Modern periodic law and the present form of the periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound uh, developments in their theories about subatomic particles in 1913. The English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. A plot of lambda under root V, where V is frequency of alpha lambda X-rays emitted against atomic number Z, gave a straight line and not the plot of under root V Vs versus atomic mass. He thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified. This is known as modern periodic law and can be stated as the physical and chemical properties of elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements Neptunium and plutonium, like actinium and protoactinium, are also found and pitch blend are war of uranium. It stimulated beneath interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived elements. You may recall that the atomic number is equal to the nuclear charge, that is number of protons and or the number of electrons in a neutral atom. It is then easy to visualize the significance of quantum numbers and electronic configurations in periodicity of elements. In fact, it is now recognized that the periodic law is essentially the consequence of the periodic variation in electronic configuration, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reactions and valence, whereas others stress the electronic configuration of elements. The modern version and so-called long form of the periodic table of the elements, figure 3.2, is the most convenient and widely used. The horizontal rows, which Mendeleev called series and called periods, and the vertical columns groups. Elements having similar outer electronic configuration in their atoms are arranged in vertical columns, referred to as groups and families, according to the recommendation of International Union of Pure and Applied Chemistry (IUPAC). And the groups are numbered from 1 to 18, replacing the older notation of groups I A to 7A, 8 I 8B, 8B, 7B, and O. There are altogether 7 periods. The period number corresponds to the highest principal quantum number small n of the elements in the period. The first period contains two in the period. The first period contains two elements. The subsequent periods consists of 8, 8, 18, 18, and 32 elements respectively. The seventh period is incomplete, and like the sixth period would have a theoretical maximum on the basis of quantum numbers of 32 elements. In this form of the periodic table, 14 elements of both 6th and 7th period, the lanthanoids and actinoids respectively, are placed in separate panels at the bottom. Nomenclature of elements with atomic numbers is greater than 100. The naming of the new elements had been additionally the privilege of the discoverer and the suggested name was ratified by the IPAC. The recent years, this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Figure 3.2, long form of the periodic table of the elements with their atomic numbers and ground side outer electronic configurations. The groups are numbered 1 to 18 in accordance with the 1984 IUPAC recommendations. This relation replaces the old numbering scheme of 1A, 7A, 7 IB, 7B, and 0 for the elements. Their synthesis and characterization therefore require highly sophisticated, costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the before collecting the reliable data on the new element, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claimed the credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Karchatovium. To avoid such problems, and the IUPAC has made recommendation that until a new element's discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots of for 0 and numbers 1 to 9. These are no shown in Table 3.4. The roots are put together in order of digits which make up the atomic number, and IUM is added at the end. The IUPAC names for elements with Z above 100 are shown in Table 3.4. 3.4, notation of IUPAC nomenclature of elements: digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nil, on, bi, tri, quad, pent, hex, sept, oct, in, N U B T Q P H S O E. Table 3.5, nomenclature of elements with atomic number above 100. Atomic number 101, anil, anium, ANU, mendelevium, MD. 102, anil, nabium, 103, anil trium, 104, anil quadrum, 105, anil pentam, 106, anil hexam, 107, anil septum, 108, anil octam, 109, anil nium, 110, anil nidam, 111, anil anium, 112, ananbium, 113, anantrium, 114, ananquadrum, 114, ananpentium, 116, ananhexan, 117, ananseptium, 118, anannoctium. Thus, the new element first gets a temporary name with symbol consisting of three letters. Later, permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or state of the country in which the element was discovered or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by IUPAC. Problem 3.1. What would be the IUPAC name and symbol for the element with atomic number 120? Now, solution from table 3.4. The roots for 1, 2, and 0 are 1 by and nil, respectively. Hence, the symbol and the name, respectively, are Aban and Unbelium electronic configurations of elements and the periodic table. In the preceding unit, we have learned that the electron in an atom is characterized by a set of four quantum numbers, and the principal quantum number small n defines the main energy level for known as shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals, SPDF. In an atom, the distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital field. In this section, we will observe direct connection between the electronic configurations of the elements and the long form of the periodic table. Electronic configuration and periods. The periods indicates the value of small n for the outermost or valence shell. In other words, successive period in the periodic table is associated with the kneeling of the next filling of the next higher principal energy level, n is equal to 1, n is equal to 2, etc. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period n is equal to 1 starts with the filling of the lowest level 1s, and therefore the two elements hydrogen 1s1 and helium 1s2. When the first shell k is completed, the second period n is equal to 2 starts with lithium, and the third electron enters the 2s orbital. The next element, beryllium, has 4 electrons and has the electron configuration 1s2 2s2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the L shell is completed at neon 2s2 and 2p6. Thus there are 8 elements in the second period. The third period, n is equal to 3, begins at sodium, and the added electrons enters third 3s orbitals. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. The fourth period, n is equal to 4, starts at potassium, and the added electrons fill up the 4s orbital. Now you may note that before the 4p orbital is filled, filling up of 3d orbitals becomes energetically favorable, and we come across the so-called 3d transition series of elements. This starts from scandium, Z is equal to 21, which has the electronic configuration 3d1 4s2. Now the 3d orbitals are filled at zinc, Z is equal to 30, with electronic configuration 3d10 4s2. The fourth period ends at krypton with the filling up of the 4p orbitals. Altogether, we have 18 elements in this fourth period. The fifth period n is equal to 5, beginning with rubidium. Beginning with rubidium in similar now to the fourth period, and contains the 4d transition series starting at yttrium. The 4D transition series starting at yttrium, that is equal to 39. This period ends at the xenon with the filling up of the 5p orbitals. The sixth period, n is equal to 6, contains 32 elements, and successive electrons enter 6s, 4f, 5d, and 6p orbitals. In the order filling up of the 4f orbitals begins the order filling up of the 4f orbitals begins with Pcerium, n is equal to 58, and ends at lutetium with cerium, then is equal to 58, and ends at lutetium, z is equal to 71, to give the 4f inner transition series, which is called the lanthanoid series. The seventh period, n is equal to 7, is similar to the sixth period, with the successive filling up of the 7s, 5p, 6d, and 7p orbitals, and included most of the man-made or man-made radioactive elements. This period will end at the element with atomic number the 118, which would belong to the noble gas family, filling up of the 5 of orbitals after actinium z is equal to 89 gives the 5 of inner transition series known as the actinoid series. The 4f and 5 of inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Problem 3.2: how would you justify the presence of 18 elements in the fifth period of the periodic table? Solution: when n is equal to 5, l is equal to 0, 1, 2, 3. The order in which the energy of the available orbitals 4d, 5s, and 5p increases is 5s is less than 4d is less than 4p. The total number of orbitals available are 9. The maximum number of electrons that can be accommodated that can be accommodated is 18, and therefore 18 elements are there in the fifth period. Group-wise electronic configurations: elements in the same vertical column or groups have similar valence shell electron configurations. The same number of electrons in the outer orbitals have similar properties. For table on the group 1 elements, alkali metals all have ns1 have valence shell electron configuration as shown below. Now thus it can be seen that the properties of the an element have periodic dependence upon its atomic number and not on relative atomic mass. Electronic configuration and types of elements. SPD of blocks. The above build-up principle and the electronic configuration of atoms provide a theoretical foundation for the periodic classification. The elements in a vertical column of the periodic table constitute constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks: YCS block, P block, D block, and F block, depending on the type of atomic orbitals that are being filled with electrons. This is illustrated in figure 3.3. We notice two exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 elements is justified because it has a completely filled valence shell 1s2 and as a result exhibits properties characteristic of other noble gases. The other exception is hydrogen. It has only one cs electron and hence we can place it in group 1 alkali metals. It can also gain an electron or achieve a noble gas arrangement and hence it can behave similar a group 17 halogen family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2. The figure and 3.3. Now we will briefly discuss the salient features of the 4 types of elements marked in the periodic table. More about these elements: lithium, sodium, potassium, rubidium, cesium, rhodium. Electronic configuration. Thus, it can be seen that the properties of the elements have periodic dependence upon its atomic number and not on relative atomic mass. We will be discuss matter during the description of their features. Certain terminology has been used which has been classified in section 3.7. Electronic configuration and types of elements, SPD of blocks. The above build-up principle and the electronic configuration of atoms provide the theoretical foundation For the periodic classification of the elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distributions of elements there in their outermost orbitals. We can classify the elements into four blocks: wise S block, P block, D block, F block, depending on the type of atomic orbitals that are being filled the electrons. This is illustrated in figure number 3.3. We notice two exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning on the P block along with the other group 18 elements is justified because it has a completely filled valence shell 1s2, and as a result exhibits the properties characteristic of other noble gases. The other exception is hydrogen. It has only this electron and hence can be placed in the group 1 alkali metals. It can also gain an electron and achieve for noble gas arrangement, and hence it can behave similar to a group 17 halogen family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2 and 3.3. We will briefly discuss the salient features of the four types of elements marked in the periodic table. More about these elements will be discussed later, and during the description of their features certain terminology has been used which has been classified in section 3.7. The S block elements, the elements of group 1 alkali metals and group 2 alkali earth metals which have ns1 and ns2 outermost electronic configuration belong to the S block elements. They are the relative metals with low ionization enthalpies. They lose the outermost electrons readily to form 1 plus ion in the case of alkali metals, or 2 plus ion in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. The P block elements comprise both belonging to group 13 to 18, and these together with the S block elements are called the representative elements or main group elements. The outermost electron configuration varies from NS2 to NP2, NP1 and NS2 to NP6 in each period. At the end of each period, there is a noble gas element with the closed valence in the closed valence shell ns2 to np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition of or removal of electrons. The noble gases thus exhibit very low chemical reactivity preceding the noble gas family. The R2 chemically important groups of non-metals, they are the halogens group 17 and chalcogens group 16. These two groups of elements have highly negative electrons, gain enthalpies, and readily add one or two electrons respectively. To attain the stable noble gas configuration, the non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. And the D block elements, transition elements, and these are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by electrons and are therefore referred to as D block elements. D block element. These elements have the general outer electronic configuration n-1, d1 to 10 on the ns, 0 to 2 except for pd, where its electronic configuration is 4d10, 5s0. They are all metals. They mostly form colored ions, exhibit variable valence, oxidation states, paramagnetism, and oftenly used as catalysts. However, zinc, cadmium, and Hg which have the electronic configuration n-1 d10 ns2 do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of s block elements and the less active elements of group 13 and group 14, and thus take their familiar name transition elements. The f block elements, inner transition elements, the two rows of elements at the bottom of the periodic table called the lanthanoids. C Z is equal to 58 LU, Z is equal to 71, and actinoids Z is equal to 90 LR. Now, Z is equal to 103 are characterized by the outer electronic configuration n minus 2 F1 to 14, n minus 1 D 0 to 1 ns2. The last electron added to each of elements are hence called the inner transition elements, F block elements. And they are all metals within each series. The properties of the elements are quite similar. The chemistry of the earlier actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoid elements are radioactive. May of the actinoid elements have may been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. Problem 3.3, the elements Z is equal to 107, 17 and 120 have not yet been discovered in which family group would you place these elements, and also give the electronic configuration in each case. Solution: we see from figure 3.2 that elements of Z is equal to 117 would belong to the halogen family group 17, and the electronic configuration would be Rn here 4f6 14 or 4 6d 10 60 0 to 60 10 7s2 7p 5. The element with Z is equal to 120 will be placed in group 2 alkaline earth, will be placed in group 2 alkaline earth metals, and will have the electronic configuration UUU the 8s2 metals, non-metals, metalloids. In addition to displaying the classification of elements into S, P, D, and F blocks, figure 3.3 shows another broad classification of elements based on their properties. And the elements can be divided into metals and non-metals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. The metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium also have very low melting point, 303 Kelvin and 302 Kelvin respectively. Metals usually have high melting point and boiling points, and they are good conductors of heat and electricity. They are malleable, can be flattened into thin sheets of malleable, can be flattened into thin sheets of hammering, and ductile, can be drawn into wires. In contrast, non-metals are located at the top right hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. Non-metals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The non-metallic character increases as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt as shown by the thick zigzag line in figure 3.3. The elements example silicon, germanium, arsenic, antimony, and tellurium bordering this line and running diagonally across the periodic table show properties that are characteristic of both metals and non-metals. These elements are called semi-metals and metallites. Problem 3.4, considering the atomic number and position in the periodic table, arrange the following elements in the increasing order of metallic character: silicon, beryllium, magnesium, sodium, potassium, phosphorus. Metallic character increases down a group and decreases along a period as we move from left to right. Hence, the order of increasing metallic character. Sodium is greater than magnesium is greater than beryllium is greater than silicon is greater than phosphorus. The periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or more move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 non-elements. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within the group of non-metals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends, and how can be explain periodicity? To answer these questions, we must to look into the theories of atomic structure and properties of atom. In this section, we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. Trends in physical properties. There are numerous physical properties of elements such as melting and boiling points, heats of fusion and vaporization, energy of atomization, etc., which show periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity, atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of the ball. Now, do you know why? Firstly, because of the size of an atom, 1.2 angstrom, that is 1.22 2 into 10 to the power minus 10 meter in radius, is very small. Secondly, since the electron cloud surrounding the atom does not have the sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. The one practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between um, two atoms when they are bound together by a single bond in a covalent molecule, and from this value the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule Cl2 is 198 pm, and half this distance is 99 pm. This taken as an atomic radius of fluorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two the adjacent copper atoms in solid copper is 256 pm. Hence, the metallic radius of copper is assigned by a value of 128 pm. For of copper is assigned the value of 128 pm. For simplicity, then in this book we use the term atomic radius for to refer to both covalent or metallic radius, depending on whether the element is a non-metal or a metal. Atomic radii can be measured by X-ray and other spectroscopic methods. The atomic radii of a few elements are listed in table 3.6. two trends are obvious. We can explain these trends in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in the figure 3.4e. For the elements of the second period, it is because within the period of the outer electrons are in the same valence shell and the effective nuclear charge the increases the atomic number increases resulting in the increased attraction of electrons to the nucleus within a family or vertical column of the periodic table. The atomic radius increases regularly with atomic number as illustrated in figure 3.4b. For alkali metals, the principal quantum number is small and increases the valence electron are further from the nucleus. This happens because the inner energy level are filled with electrons which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of noble gases are not considered here being monoatomic. Their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of other elements. Ionic radius. The removal of electron from an atom results in the formation of cation, whereas gain of an electron leads to an anion. When we find some atoms and ions which contain the same number of electrons as we call them isoelectronic spaces. Ionization enthalpy. The quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. 3.6a graph first ionization enthalpy delta H of elements of the second period and as a function of atomic number Z and figure 3.6b delta H of alkali metals as a function of Z. 3.5 figure variation of first ionization enthalpy is delta H with the atomic number of elements so Z is equal to 1 to 60. Valence electron in an atom will be less than the actual charge on the nucleus because of shielding and screening of the valence electron from the nucleus by the intervening of core electrons. Electron gain enthalpy. When an electron is added to a neutral gaseous atom X to convert it into a negatively ion, the enthalpy change accompanying the process is defined as electron gain enthalpy delta H. Electron gain enthalpies kilojoules per mole of some main groups of elements table 3.7. Hydrogen, lithium, sodium, potassium, rubidium, cesium, oxygen, sulfur, psyllium, tritium, beryllium, phosphorus, chlorine, bromine, iodine, atium, helium, neon, argon, krypton, xenon, radon. Electronegativity. The qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. Periodic trends. The table 3.8 electronegativity values on Pauling scale across the periods. 3.8b electronegativity values on Pauling scale down of family. Periodic trends in chemical properties. Periodicity of valence or oxidation states. 3.9 table. Periodic trends in valence of elements are shown by the formulas of their compounds. Anomalous properties of second period elements. Periodic trends and chemical reactivity. Classification of elements and periodicity in properties, then summary. In this unit, you have studied the development of the periodic law and the periodic table. Mendeleev's periodic table was based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers and gives 7 horizontal rows, periods, and 18 vertical columns, groups, or families. Atomic numbers in a period are consecutive whereas in a group they increase on pattern elements on the of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally the increasing number of electrons recognized in the periodic table on the basis of their electronic configuration. These are S block, P block, D block, and F block elements. Hydrogen with one electron is in the 1s orbital occupies a unique position in the periodic table. Metals comprise more than 78% of the known elements. Non-metals which are located at the top of the periodic and non-metals are examples table are less than 20 in number. Elements which lie at the border line between metals and non-metals, example silicon, gallium, astrium, are called metalloids and semi-metals. Metallic character increases with increasing atomic number in a group, whereas it decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic mass, atomic size, ionization, enthalpies, electron gain, enthalpies, electronegativity, and valences. Now, the atomic radii decreases while going from left to right in a period and increase the atomic number in a group. Ionization enthalpy generally increases across a period and decreases down a group. Electronegativity also shows now a similar trend. Electron gain enthalpy in general become more negative across a period and less negative down a group. There is some periodicity of valence, for example, among outermost orbitals or 8 minus this number. Chemical reactivity is highest at the 2 is because of the ace of electrons loss or low ionization enthalpy. Highly reactive elements do not occur in nature in free state. They usually occur in the combined form. Oxides formed of the elements on the left are basic and of the elements are the right and acids the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. Classification of elements and periodicity in properties. अच्छा, क्लासिफिकेशन ऑफ एलिमेंट्स एंड पीरियोडिसिटी इन प्रॉपर्टीज़ में हमने पहले से देखा. थर्ड यूनिट है हमारा 11th क्लास केमिस्ट्री स्टार्ट है और यहाँ पर हमने थर्ड यूनिट कंप्लीट कर दिया है. क्लासिफिकेशन ऑफ एलिमेंट्स एंड पीरियोडिसिटी इन प्रॉपर्टीज़. व्हाई डू वी नीड टू क्लासीफाई एलिमेंट्स. इसमें हमने देखा जेनेसिस ऑफ पीरियोडिक क्लासिफिकेशन, देन डोब्राइनस ट्राइड्स एंड न्यूलैंड्स ऑक्टेव्स. देन उसके बाद हमने देखा मॉडर्न पीरियोडिक लॉ एंड द प्रेजेंट फॉर्म ऑफ द पीरियोडिक टेबल. देन उसके बाद हमने देखा नॉमेनक्लेचर ऑफ एलिमेंट्स विद एटॉमिक नंबर ग्रेटर दैन 100. देन उसके बाद हमने देखा नोटेशन ऑफ IUPAC और नॉमेनक्लेचर ऑफ एलिमेंट्स. देन नॉमेनक्लेचर ऑफ एलिमेंट्स विद एटॉमिक नंबर अबव 100. Then electronic configurations of elements and the periodic table. Then electronic configuration in periods, group wise electronic configurations, electronic configuration and types of elements, SPDF blocks, the S block, P block elements, D block elements, and F block elements, metals and non-metals, non-metals and metalloids. Periodic trends and properties of elements, trends in physical properties, atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, electronegativity. Electronegativity values on Pauling scale across this period. Electronegativity values down a family. Periodic trend in chemical properties. Periodicity of valence or oxidation states. Anomalous properties of second period or elements. Periodic trends as and chemical reactivity. Then summary. सो प्लीज़ लाइक शेयर, ज़्यादा से ज़्यादा लोगों तक शेयर कीजिएगा इस वीडियो को, क्योंकि हमने वन शॉट सीरीज स्टार्ट की 11th क्लास केमिस्ट्री के और इसमें हमने पूरा चैप्टर कंप्लीट कर दिया. यूनिट 3 क्लासिफिकेशन ऑफ एलिमेंट्स एंड पीरियोडिसिटी इन प्रॉपर्टीज़. प्लीज़ लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग.